Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to go ahead and look at ice tables, which is a fancy tool we use to describe equilibrium reactions and has nothing to do with making an actual table out of ice. So one of the big things when we're trying to look at an equilibrium reaction is that Q helps us figure out which direction a reaction occurs. However, what it doesn't tell us is the exact composition of that reaction. So what we need to do is figuring out how much of our reactant ends up becoming product or product becomes reactant. Now, Q will help us determine which way the reaction goes, and that will end up helping us as we go forward. But let's go ahead and look at this example of the transformation of cis-stilbene to trans-stilbene. This is called an isomerization reaction. We're going from one isomer of a compound to another isomer. These are very important in chemistry as each of these compounds will have different reactivity. But they're also good illustrative examples because it is a one-to-one reaction. And you'll note that the equilibrium constants tend to be fairly even. It's just as likely one form is rarely that much favored over another, so they're relatable. This is going to be useful as we're going to try and look at what happens if I throw 1 mole of cis-stilbene into a 1 liter container. So this means I'm working with 1 molar cis-stilbene, and now I want to try and figure out how many moles of cis-stilbene will end up transforming into trans-stilbene once we reach equilibrium. And we can base this on the initial amounts of each species. So I'm going to start with 1 mole of cis-stilbene and 0 moles of trans. And now I need to figure out essentially whether the reaction ends up increasing or decreasing each species and by how much. And we're going to do this using what's called an ice table. So this is based on initial, change, and equilibrium. So let's start with initial conditions. I'm going to start with 1 mole of cis-stilbene and 0 moles of trans. So this means that I'm going to have the reaction go to the right. So I'll be generating trans. So I'm going to represent this using the extent of reaction. So for convenience here, I'm going to represent it with an X. It's also technically correct to represent this with a chi, and you'll see a lot of textbooks use one or the other. So we've seen chi show up once or twice in some of our figures, and that's because we're looking at how many moles of reaction has occurred. So in this case, this reaction, for every chi moles it progresses, I'm going to consume that many moles of cis and produce that many moles of trans. So relatively straightforward. We're looking at the relative change. So this means that once I eventually reach equilibrium, it's going to be whatever I started with minus however much I lost and however much I started with plus how much I gained. So that's the reason why representing the signs on that change column can be really important. However, one of the things that is worth noting is since the volumes of all of these systems are going to be the same, we don't have to represent them as moles. We can represent them as molarity. Now, do note that this only occurs if both reactants and products are in the same container, which is usually the case. Gets a little bit messy if I'm having a gas-producing reaction, though. And that volume doesn't change. So I'm not generating or consuming a fair amount of my solvent. So in this case, we can use molarity instead of moles, which is fairly convenient. But watch out for trying to do this where we have the reactants and products in different phases. So in these cases, I can represent my ice table now in terms of molarity instead of moles. And the reason why this is so useful is I can now relate it to my equilibrium constant. So I know that my equilibrium constant is going to be products over reactants. Well, I know at equilibrium, I should have X moles of trans and 1 minus X moles of cis. So that gives me the concentrations of products and reactants in terms of a single variable. I know 1 is a constant, and turns out so is my equilibrium constant. Again, it has a value of 24, so we're favoring products over reactants. So now what I can do is, using this equilibrium constant, I can go ahead and try and solve for my extent of reaction, so this X value. So I can do that by moving my 1 minus X over to the left-hand side, so multiply both sides by 1 minus X. So when I've got 24 times 1 minus X equals X. So we can go ahead and distribute this 24, and we have X is equal to 24 molar minus 24X. So what we can now do is clump all of our X's to one side. So I'll add 24 on this side. That cancels out that value and turns this guy into 25X equals 24 molar. So then I divide both sides by 25, and it turns out X has a value of 0.96 molar. So yay, I know my extent of reaction. Why is this useful? This is because I can now use this extent of reaction to plug back into my ICE table and solve for all of my molarities. So when I do this, I still have the same initial, but now my change is minus 96 and plus 96. Now this gives me an equilibrium value for cis of 0.04 molar and 0.096 molar for trans. And from this, we note that turns out I turned most of my reactants into trans-stilbene. That's pretty cool, but it also makes sense. And it's always worth making sure your ICE table passes the smell check. My equilibrium constant has a value greater than 1, which means I favor products. And I favor products about a 24-to-1 ratio. And that's exactly what I see here. So it's always worth double checking to make sure your favoring of products or reactants agrees with what you see with the equilibrium constant. One of the things that is worth noting, though, is that this simple treatment only ends up working for a 1-to-1 transformation. We have to be a little bit more careful once we start including stoichiometric coefficients. So next time, we're going to go ahead and start working with a little bit messier ICE tables. Until then, take care.